So this numerator is of the form a minus b times a plus b, right? Conjugate of a minus b is a plus b. And you know when you FOIL that, you get a difference of squares. A squared minus b squared. Okay? That's from section 1.5. So when we FOIL this numerator, right? Product of the first terms, set square root times the same square root, right? That's equal to 2x plus 2h minus 5, right? When you multiply this square root by itself, the square root goes away. And then when we do the last terms, you get minus times a plus, which is minus, and then times square root of 2x minus 5 times square root of 2x minus 5 is 2x minus 5. Okay. And when you do the inner and the outer terms, they cancel. Okay. That's why it ends up being a squared minus b squared, because the inner and the outer terms cancel. And so this is equal to, denominator again, h times the square root 2x plus 2h minus 5 plus the square root 2x minus 5. Okay? Well, you know, you got to now distribute the minus sign inside the parentheses. And when we do that, we have 2x plus 2h minus 5 minus 2x plus 5 all over that denominator. H times the square root 2x plus 2h minus 5 plus the square root of 2x minus 5. Well, in the numerator, 2x minus 2x is 0, and minus 5 plus 5 is 0, and we're just left with 2h in the numerator. Okay? So this is equal to denominator, we have h times the square root 2x plus 2h minus 5 plus square root of 2x minus 5, and then the numerator we just have 2h, 2 times h. Okay? Is there a common factor in numerator and denominator? Certainly. H over h cancels. And so, our difference quotient after it's been rationalized is equal to square root 2x plus 2h minus 5 plus plus the square root 2x minus 5 in the denominator. 2 in the numerator. So we have 2 divided by this denominator as our difference quotient after it's been rationalized. And now to find the derivative f prime of x, we take the limit as h goes to 0 of the difference quotient. The limit is h goes to 0, 2 over the square root 2x plus 2h minus 5 plus the square root 2x minus 5. And now we do the direct substitution. Put in 0 in for h. So we have 2 over the square root of 2x plus 2 times 0 minus 5 plus the square root 2x minus 5. Well, 2 times 0 is 0, and we're just left with the square root of 2x minus 5 plus square root of 2x minus 5. Those are like radicals, so this denominator is equal to 2 times the square root of 2x minus 5. Well, the 2's cancel. And we're just left with 1 over the square root of 2x minus 5. So the limit exists. And it's equal to 1 over the square root of 2x minus 5. Okay? It's nice that you guys get to watch me record myself. And that wasn't the intention at all. Okay, that's the intention. Okay. I didn't realize that. Okay. So the derivative of this function, f of x, is equal to, what is f prime of x, which is equal to 1 over the square root of 2x minus 5. Okay. And you'll be doing a lot of this type of thing in Calc 1. Okay. All right. Any questions on that? Okay. So if you flip over your page, I told you to scratch this out and put it on the back of page 3, right, on page 4. Because I used the whole page. You're calculating the derivative in A. So in B, our function is f of x is equal to x cubed minus x, okay? So we got to construct the difference quotient. So first step, calculate f of x plus h. And f of x plus h is x plus h cubed minus x plus h in parentheses. All right, we just replace x and f of x with x plus h. And then this to expand this, right, you gotta use from section 1.5 the binomial expansion for n equals 3. And when you do that, it took me a second, right? You guys talk about having to remember all these formulas. It took me a second to recall it, but I did. X plus h cubed is equal to x cubed plus 3hx squared plus 3h squared x plus h cubed and then when we distribute the minus sign inside parentheses, we have minus x minus h, okay? And there are no like terms in that, okay? So step 2, calculate f of x plus h minus f of x. So f of x plus h minus f of x is all of this. X cubed plus 3h x squared plus 3h squared x plus h cubed minus x minus h. And then we subtract f of x. And since there's more than one term in f of x, put it in parentheses so you won't distribute the minus sign correctly. And now, distribute the minus sign. We get x cubed 3h x squared plus 3h squared x plus h cubed minus x minus h minus x cubed plus h. And this is a polynomial, right? So when you subtract f of x from f of x plus h, all the terms in the polynomial should cancel. And you notice we have x cubed minus x cubed minus x plus x, right? They all cancel. And so we're left with 3h x squared plus 3h squared x plus h cubed minus h for f of x plus h minus f of x. So to finish the difference quotient, we now have to divide left and right hand side by h. So f of x plus h minus f of x over h. Divide the left hand side by h, divide the right hand side by h. And when we divide the right hand side by h, each of those terms have to be divided by h, right? Because division does not undo addition and subtraction. So we have 3h x squared over h plus 3h squared x over h plus h cubed over h minus h over h, which is equal to, right? H is canceled in this first fraction. We're left with 3x squared. H squared over h, using the rules of exponents, is just equal to h. So we have plus 3hx. H cubed divided by h is h squared. And h divided by itself is 1. So the difference quotient for this problem is equal to 3x squared plus 3hx plus h squared minus 1. Okay. And now we can calculate the derivative. F prime of x is equal to the limit as h goes to 0 of the difference quotient which in this case, right, so this is equal to the limit as h goes to 0 of the difference quotient, which in this case is 3x squared plus 3hx plus h squared minus 1. And now we do the direct substitution. And remember, we do the direct substitution for h, not x. It's h that's going to 0. So we have 3x squared plus 3 times 0 times x plus 0 squared minus 1. And so we end up f prime of x is equal to 3x squared, 3 times 0, 0, 0 times x is 0, 0 squared is 0. And so you just end up with 3x squared minus 1 for the derivative. And we're done. Okay. Yes, ma'am.
Is the limit always going to be 0
for h?
Yeah.
Yep.
Okay.
It always, right? That's in the definition at the bottom of page 2, right? The limit as h goes to 0, the difference quotient. Okay. So you can see that finding the derivative was a lot easier for this polynomial than it was for something containing a radical. Radicals require a lot of work, a lot of algebra. Okay? Polynomials are easier to deal with. All right. So you have everything you need to successfully complete this homework assignment, which is due tomorrow night. Okay? All right, so now let's move on to a new topic known as polynomial functions. Let's see. Kelly, is there somebody sitting behind you? No, that's you, Slowly. So we hand Kelly one, please. Let's see. Emma, you don't get one, right? This girl does. Miss, will you give Mr. Ogburn one, please? All right. Polynomial functions. So I remember studying polynomial functions in high school. Maybe you do too. It's a popular class of functions to study. Okay. And so here we began at the top of page 1 with the definition of a polynomial function. N has to be a non-negative integer, right? So non-negative is 1, 2, 3, 4, 5, 6. So it can include 0, 0, 1, 2, 3, 4, 5, 6, so forth. Okay. A polynomial function of degree n is a function defined by this notation. Okay? A sub n times x to the n, right? And the next term has x to the n minus 1, and then on down to x squared, x to the first, and then a constant term. These a's are real numbers, and they're called the coefficients of the polynomial function. This term here with the largest power of n is called the leading term of the polynomial. And so it has the largest power of n. So n is the degree of the polynomial, and a sub n is called the leading coefficient. So some examples of functions that are not polynomials is f of x equals 5x squared minus 3 times x to the minus 1, right? So the coefficients are 5 and minus 3. Now, 2 is a positive integer, but minus 1 is not, okay? So this is minus 1, right, is a negative integer. So this is an example, and you can write this at the top of your paper if you want, right? Up here, very top. This is an example of a function that is not a polynomial function. Okay? Another example is f of x equals 2x to the 1/2 power minus 4. This is another example of a function that's not a polynomial function. Even though the exponent on the variable x is positive, it's not an integer. Okay? The 1/2 is not an integer. Okay? The exponent on the variable x has to be positive. So in example 1, okay, these two are examples of polynomial functions. Right? The power in each term involving x, right? The exponent on the variable x is a positive integer. Okay? So in the first example, 4x to the 5th plus 6x cubed minus 2x plus 1. Okay. To determine the degree, the leading coefficient of the given polynomial functions. Well, the largest power of x in this example is 5. So n equals 5 is the degree. And the coefficient in front of x to the 5th is 4. And so 4 is the leading coefficient. Okay? In B, we have 2x squared minus 3x plus x cubed minus x to the 7th. Well, the largest power of x in this example is 7. So n equals 7 is the degree of this polynomial. And the leading coefficient is the number in front of x to the 7th. Well, this minus sign is actually a -1, right? This is -1 times x to the 7th. So -1 is the leading coefficient. Okay? So those are two examples of polynomial functions, and that's how you determine the degree and the leading coefficient. You look for the largest power of x to get the degree, and the number in front of the largest power of x, right? In front of that x term is the leading coefficient, okay? A power function of degree n is a polynomial of the form, so we're talking about a power function of degree n, is a polynomial of form f of x equals a times x to the n, okay? Again, a is a coefficient, right? It's a real number, okay? And n is a positive integer. The graph of the polynomial function is continuous, and you might add after that statement the domain of a polynomial function, or all polynomial function, is what? Does anybody remember? From our high school days, maybe? It's all real numbers. Minus infinity to plus infinity. You can put in any real number in for x in a polynomial function, okay? And the right-hand side, value the right-hand side would be a real number, okay? All right, in general, we're going to look at the shape of this power function for different degrees n, and whether the leading coefficient, the coefficient in front of x to the n, is positive or negative. Okay? So we're going to draw 4 graphs. In the first graph, a is positive, and the power of x is even, right? So you know 2, 4, 6, 8, so forth are examples of even integers. Okay? Well, if n is even and a is positive, okay, so let's remind ourselves, we're looking at f of x equals a times x to the n power. Okay? If a is positive and n is even, the graph is U-shaped, kind of like a parabola. It is a parabola if n equals 2. It's just U-shaped if the n is 6, 8, 10, 12, right? Other even integers. If a is negative, less than 0, and n is even, like 2, 4, 6, 8, so forth, then the graph of this function f of x equals a times x to the n is U-shaped, but it's an upside down U. Okay? If a is positive and n is odd, like 3, 5, 7, 9, so forth, okay, then the graph of this function f of x equals a times x to the n will be similar to the cubing function, right? Left end goes down, right end goes up. And if a is negative, last graph, and n is odd, then the graph is flipped over. The left end goes up and the right end goes down. Okay? Any questions on that? Yes, ma'am.
Is that an x-axis flip or a y-axis flip?
X-axis. Yeah. Well, in this case, hold it, let me rephrase that. It's the same. You end up with the same graph.
Okay.
Whether it's flipped over the x-axis or flipped over the y-axis in this case. Okay. Over here, it's definitely flipped over the x. But over there, you flip it over the y or flip it over the x, you get the same thing. Okay. All right. So why am I talking about this? Because these four graphs, and looking at what is called the end behavior of the graph of a polynomial function, right? This will help us determine what the end behavior is, okay, for the polynomial function. But we're going to do a lot of graphing here at the bottom. We're going to draw four graphs, and so I think we'll just wait and get started on that. I don't want to start it and stop, so we'll just stop right here for today, okay? And remember, we got a short quiz tomorrow, okay? So I'll see you tomorrow.